Welcome back to Molecular Machines for Dummies. Today we are going to be discussing a major part of the mitochondria, the mitochondrial ribosome, or the mitoribosome. There are ribosomes that exist in the cytosol and synthesize the majority of your body's proteins. There are also ribosomes that are present in the mitochondria. These ribosomes differ from the cytosolic ribosomes in both the kind of proteins they synthesize and their structure. These differences are likely a result of evolution, as the mitoribosome is a descendant of bacterial ribosomes. While cytosolic ribosomes produce the majority of your body's proteins, the mitoribosome synthesizes a few vital proteins, the majority of which are involved in the electron transport chain and ATP synthase.
The mitoribosome in adult mammals consists of a large subunit called 39S and a small subunit called 28S, which come together to form the mitoribosome complex 55S. The S means Svedberg unit and simply indicates how a molecule sediments when it's centrifuged. The Svedberg unit usually correlates to size, but if a molecule is elongated, such as the mitoribosome, it can have a smaller S than similarly sized molecules that aren't elongated. The mitoribosome is composed of both RNA and proteins, but compared to its bacterial counterpart, the mitoribosome has a higher protein to RNA ratio for the synthesis of oxidative phosphorylation specific proteins.
The mitoribosome's function is to synthesize proteins. This process begins when mRNA is fed into the 55S mitoribosome. mRNA is the code that the mitoribosome reads, and tRNA is a decoder which tells the body which amino acid, the building blocks of proteins, should be added to the nascent polypeptide chain. The tRNA has a specific amino acid attached to it, and the mitoribosome catalyzes a reaction that joins amino acids. There are three phases of translation, the process of creating proteins, that end with a completed protein. These phases are initiation, elongation, and termination. The phases repeat, adding more and more amino acids until the protein is complete.
The mitoribosome produces many of the complexes in the ETC and ATP synthase. Therefore, if the mitoribosome malfunctions, there can be disastrous effects similar to what we discussed regarding ATP synthase defects in the last video. A mutation in the mitoribosome can result in a variety of symptoms, as the majority of energy production in the body would stall. How these mutations are phenotypically present often vary depending on the specific mutation, but generally, these mutations involve childhood onset brain abnormalities, cardiac malfunctions, increased lactate levels, and respiratory chain deficiencies. The brain and the heart are consistently affected by mitoribosome mutations, as both of these organs require a high amount of ATP which cannot be produced when the mitoribosome is functioning. Thanks for watching.